Hello everyone, my name is Usman and I'm going to go over our project on electrical power systems for WINSAT team. Just to give you an insight what WINSAT team is all about, it's basically a multidisciplinary engineering team taking part in Canadian Space Design Challenge Competition 2018-2020. It's basically a national competition for Canadian universities to design, test and build a 3U CubeSat for mission in low Earth orbit. Basically, electrical power systems division is divided further into two subdivisions, one of them being power estimation, the other one being designing of printed circuit boards. So as you can see on my right hand side of the poster, you can see a couple of designs for our PCB. One of them is for payload module and the other one is for solar panels as well. So, and there were others as well that were designed for ADCS and PC104 layout. They were unfortunately not printed because of the global conditions. Uh, so we were able to successfully design about roughly about 4 to 5 PCB boards. And next up, for power estimation, there were two major parts that were done. One of them was checking the power generation through STK11 simulation, and the other one was creating a battery integrator in Simulink to mimic the battery and our EPS module to check the charging and discharging condition under nominal conditions. So let's go over our Simulink model first. So this is what our Simulink model looks like. So as you can see, there is a PV array on our left hand side, and it has two inputs, one of them being temperature of the cells, other one being irradiance. So what irradiance is basically just the watt per meter square, which is basically power over area. So we can get all these data from our STK simulations as well. And you can see there are certain values that were calculated for our solar cells by looking at some of the data sheets and gathering some information. So at present, this particular solar array module is basically producing about 17.8455 watts for our battery. Our battery that was selected was basically rated at capacity 30 watt hour, and it has a nominal voltage for 8.3 volts. And being a space rated battery, we had to select this battery before running our simulations. For that, we did create a power budget data sheet which helped us to determine what kind of a battery would be suitable for our conditions. As you can also see, there is a load that is a fixed load in our circuit, so we can alter it as per our conditions. So let's look at some of the major things that was really important was the breaker. So this breaker was installed to mimic the characteristics of our EPS module. So what this we'll further see what this breaker does. It basically protects the battery from being overcharged. So overcharge protection, which our EPS module is capable to do. So let's look at a sample result that we did run. So this particular simulation takes a long time to run, and it takes about like 1 to 2 hours to charge up to like 10 to 15% of the battery. So as you saw, like our battery input is dependent on the irradiance. So as you can see, when the irradiance was initially 0, our initial state of charge of the battery was 80. So it started to drop from 80 and started to discharge the battery because the irradiance, there was no power generated by the solar panels. So the state of charge kept on dropping until it hit about roughly around like 900 irradiance watt per meter square. The battery started to gradually increase, and state of charge gradually started to increase and charge up the battery. As you can see, when it hit about like 1800, at 80, roughly around 79.89 or 79.9, our battery started to rapidly increase and charge up the battery. So as we talked about the breaker, so as a breaker helps is basically EPS module has a cutoff. So for example, the cutoff is for our APS for our battery is 81%. So whenever the battery is charged up to 81%, it would basically disconnect the solar panels from our battery to protect it from overcharging. So as you can see and observe, the SOC levels basically stays constant after it reaches at 81, where and the breaker is basically switched to 0. So it's basically kind of like an open circuit in that point. So let's start the SDK simulation part. So firstly, we go to Blender and render down the faces. And basically what it does is it basically just keeps the satellite solar panels intact and just remove each and every component within it. It basically helps during our simulation because if we have major components inside, it would basically take more time for our simulation to be completed. Next up, let's go to the SDK simulation part. So this particular simulation is set for winter solstice. So we did different scenarios to determine the power generation. So there were two major orbits. One was ISS orbit, and the second one was sun synchronous orbit. So basically, we can select the orbits from this particular window. So you can see this particular simulation is set for sun synchronous orbit at an altitude of 400 kilometers, and we do have the local time of descending node as well. So this is what the 2D graphics of our orbit looks like. So let's go ahead and run a simulation. So this is how in the 3D graphics our satellite would appear. So you can see like it's pretty much similar to one that Blender has, and it's basically rendered down as well. So you can see there's no component inside. Okay, so let's go ahead and run the simulation. So we'll go under the solar panels. So we'll have like two major part over here. We can create area as well, or we can also calculate area through this, and as well as power generation. Both of those things would be really helpful for us. So you can see our satellite over here, and we have like different faces. So solar cells facing antenna to the right represents as FAR, facing antenna to the left. So if you see our satellite over here, so this is how our satellite looks. So facing antenna to the right means the solar cells on this side. So that's how it would run. And for running, just we'll simply select all of these. And we do have data for one orbit, so winter solstice. So we can find all these data on NASA's website as well. So we can have like 21st December 2020, and from 5:02 it would run until one whole day. So let's compute the data. So as we want to just generate power, we'll select power, and we can also get a report of it. So we can have like timestamps of every 10 seconds. So the satellite would collect all the data from every 10 seconds. So we'll just hit compute. So just after the simulation is completed, we can generate a graph which would basically show us the different data that has been calculated. So from this chart, you can observe there are four different data sets over here. So solar cells towards right, facing antenna from the right, left, downwards, upwards, and all solar panel groups in general. So you can see like if you see the total power that was generated in this particular solstice in sun synchronous orbit is roughly about 8 watts. So you can see why didn't we consider having solar panels on the four sides is because if you see FAD, it's really small and negligible. So and it's not really efficient as well. It's just generating 1.2 1.4 watts. So that's why we neglected that particular side, and we decided just to go with three solar panels on just the three sides. Thank you for watching. Have a good day.